Hello everyone, welcome to the course on Fundamental of Electronics Engineering. This is lecture 4 and in this lecture we will see some practical applications of OPAMP. So we have several applications. First is the inverting amplifier, next is the non-inverting amplifier, unity gain amplifier, summing amplifier, difference amplifier, integrator, differentiator, and finally we will be seeing the comparators. So in the last lectures we have seen that in the operational amplifier, once it is operated in the open loop configuration, it is provided with the very high gain. So we are not able to utilize that huge amount of gain. So what we did is we just made a feedback, and with the help of that negative feedback we decreases the gain of the OPAMP, or we can say the advantage of decreasing this gain is the stability of the circuit increases. So in this lecture we will see various applications of OPAMP, and these applications basically deal with the negative kind of feedback. So very first application is a inverting amplifier. As the name suggests, inverting means if the input is applied at the inverting terminal of the OPAMP, so this particular configuration is known as inverting amplifier configuration. Also we can see that this feedback is applied at the negative input terminal of the OPAMP. That's why it is known as the negative feedback configuration. So our aim is to find a relationship which is for the output versus input. So for this particular circuit, how can we find out the output relationship? So we are utilizing the virtual ground concept. So we have already seen that what is virtual ground. So virtual ground is something different from the actual ground. So what we have seen that in case of virtual ground, we say that no current is entered into the input terminal of the OPAMP because the input impedance of the OPAMP is very high. So if the input impedance of the OPAMP is very high, that means the potential of both the negative and the positive terminal, which is the inverting and the non-inverting terminal, are same. So if we'll utilize this concept, this virtual ground concept, and with the help of KCL, we'll be able to derive the relationship for output voltage. So if let's say if this is connected to ground, so we can say that using virtual ground, the potential at X is also 0. And after that, if we'll apply the KCL at this particular node X, so we'll be having 0 minus of V1 divided by R1 plus 0 minus of V0 divided by RF, and we have seen that no current is entered into the input terminal of OPAMP. That means whatever the current here, that will be bypassed through the feedback resistance RF. So this is equal to 0. And if we'll further simplify, this is V0 by V1 equals to minus of RF divided by R1. Or we can say, if we can denote this as V in, so we'll be having V0 divided by V in equals to minus RF by R1. So this basically minus sign signifies that there is a negative sign, shows that there is a phase shift of 180 degree between input and output voltage. Also, the voltage gain of a inverting amplifier is given by minus of RF divided by R1. So these are the two key points which we achieve while implementing this inverting amplifier. So as we can already see here that AV equals to minus of RF by R1. So RF is something, the resistance which is in kilo ohm, let's say around 100 kilo ohm. R1 is generally of the order of, let's say, 10 kilo ohm. So we'll be having a gain, let's say, AV of minus 10. Minus shows that there is a phase shift of 180 degree between input and output, where the magnitude is 10. So what we achieved is, we achieved a gain which is very less as compared to the open loop gain. Next circuit is known as a non-inverting amplifier. So as the name suggests, it's a non-inverting, means the input is applied at the non-inverting terminal of the op-amp. So let's say if I'm writing here as V in, so again we need to find out what is the final expression for output voltage. So if this voltage is V in, we can say that the other node or the other terminal of the op-amp is also connected to the same potential because of virtual ground. We have already seen in our last slides that virtual ground is that no current is entered into the input terminal of the op-amp. That's why the potential of both the terminals it appears to be same. So it is not exactly same. It is not exactly same means it is virtually, we can say it is same. So we can say virtually ground or virtual short. So now I am applying KCL at this particular node by assuming that no current is entered into the op-amp. So we can say that V input minus of 0, this current, and here the current is like this. V in minus of 0 divided by R1 plus V in minus of V0 divided by RF equals to 0. So if we try to solve that what is V0 by V in, so we achieved V0 by V in equals to 1 plus RF by R1. So here again two key points are there. That first is the voltage gain of the non-inverting amplifier is 1 plus RF by R1. Also, the phase difference between input and output voltage is 0. Means if we are providing a signal, input signal of this type, so definitely the output signal is also in the same phase. Same phase means there is a phase shift of 0 degree. So now the next application after this non-inverting amplifier is the unity gain amplifier. So unity gain amplifier, it is also known as voltage follower circuit. We'll see that why this is known as voltage follower circuit, or it is also called as unity gain buffer. As the name suggests, unity gain means the voltage gain for this particular circuit is 1. Now how can we make this unity gain amplifier? We can see here that the best possibility is how can we put the values of RF and R1. So the best possibility for this RF and R1 is RF is basically 0 and R1 is infinite. So if we'll put this RF equal to 0 and R1 equals to infinite in the previous circuit, then we have a circuit which is called as unity gain. So why it is called as unity gain? We can clearly see. Let's say if this is input, V input, so accordingly this voltage is also V input and V output is same as V input. We can write down that V output is same as V input, or the voltage gain which is AV equals to V0 by V in, the value is 1. So the voltage gain of this particular circuit is 1, that's why it is a unity gain amplifier. Now the advantage of this unity gain amplifier is this, it is also known as voltage follower circuit and it is used in the impedance matching circuits. Impedance matching or isolation, circuit isolation. We are already familiar with this voltage follower circuit or the unity gain amplifier, the common collector configuration of BJT. It is also having the voltage gain of 1. So the application of both that common collector configuration and this unity gain amplifier are the same. They are used in the impedance matching circuits. So the quality of the circuit is that input impedance is very high, which is of the order of, let's say, mega ohm, and the output impedance is very small. So that is the quality, that is a requirement for an impedance matching circuit. Now the next application of op-amp is a summing amplifier. As the name suggests, summing amplifier means if we are applying different voltages like say V1, V2, V3 to a particular op-amp, so the output is something V1 plus V2 plus V3. So this summing amplifier are also known as adder circuits. So let's say first of all we have the feedback which is negative feedback How can we make this summing amplifier or the adder circuit? We have, let's say, 3 branches, R1, R2, R3, and we have connected these resistances with V1, V2 and V3 voltages like this. And since this is grounded, so accordingly the potential of the inverting terminal is also 0. So how can we derive the relationship of V0? We'll be applying the KCL at this particular node. So we have 0 minus of V1 divided by R1 plus 0 minus of V2 divided by R2 plus 0 minus V3 divided by R3 plus 0 minus V0 divided by RF, the algebraic sum of all the current meeting at a point equals to 0, that is KCL. So if we'll further simplify this, and we can write down V0 equals to minus of RF V1 by R1 plus V2 by R2 plus V3 by R3. So this is a generalized result for a summing amplifier. So if we have, let's say, more than 3 voltages like V4, V5, so the result will be further, will be having V4 by R4 plus V5 by R5 and so on. Now the specific case, that if R1 equals to R2 equals to R3 and they are equal to the feedback resistance RF. So what result we can achieve is V0 equals to minus of V1 plus V2 plus V3. So we are getting a result which is the addition of different various voltages, which is V1, V2, V3. So it is a adder circuit. Now we can also see this mathematical expression. It is having a negative of V1 plus V2 plus V3. So this negative sign again shows it is the inverting summer. It is performing the addition but with negative sign. So it is the inverting summer. Means we can design the non-inverting summer also by putting this particular branch at non-inverting terminal and this is connected to ground like that. With the resistance, let's say some R resistance is there. So we can draw the non-inverting summer also. Now after this adder or the summing amplifier, we have the next application which is known as a difference amplifier, which is also known as subtractor. So as the name suggests, subtractor, so it is basically performing the subtraction of the input voltages applied at the inverting and non-inverting terminal. So we can clearly see that here we have voltages V2 and V1 which is applied at the input terminal of OPAMP, and we have some relationship which is of R3 by R1 V2 minus V1 type. How can we define this type of relationship? How can we achieve this kind of relationship? So the method is quite easy. Means if we are able to basically derive VA or VB, or the easiest approach is the use of superposition theorem. Superposition theorem says that if a circuit is having 2 or more than 2 sources, so the response of the circuit can be calculated due to individual sources. Means first we will be calculating V01 due to, let's say, V1, next we will be calculating V02 due to the second source V2, and after that we will be just summing up both the responses. So first of all, when V1 is applied and V2 was open circuit, so the output is V01 equals to, it is nothing but a inverting amplifier, and the gain of the inverting amplifier is minus of R3 by R1 multiplied by V1. This is first equation. Now if, let's say, V2 is applied and V1 is absent, so if V2 is applied, we can clearly see that it is nothing but a non-inverting amplifier. And for that non-inverting amplifier, we have already computed the output voltage, and the expression was 1 plus Rf by R1, means 1 plus R3 divided by R1 multiply by the voltage, which is VB. This is, let's say, equation number 2. Now, if we are able to find one more relationship, which is V2, which is between V2 and VB, then it will be quite easy. So, as we can see that no current is entered here, that means these two resistances R2 and R4, they are in series. So, the value of VB can be written as V2 multiply by R4 divided by R2 plus R4, like this. So, we'll be putting this value of VB in this equation number 2, and by utilizing that overall output V0 is the addition of V01 and V02. And further we are fixing some values, some parameters like R2 is equal to R1 and R4 is equal to R3. If we'll put these R2 equal to R1 and R4 equal to R3 in this expression, let's say equation number 3, then we are able to achieve V0 equals to R3 by R1 V2 minus V1. And if we'll put some further approximation, which is, let's say, R3 equals to R1, then we are having V0 equals to V2 minus V1. So we are getting an output expression which is the difference of two voltages, V2 and V1. So next application here is the integrator. So as the name suggests, integrator, so whatever the signal we are providing, the OPAMP is able to integrate that particular signal, which is input signal. So first of all, we are having this integrator and the differentiator circuit with the help of capacitor and an inductor separately. So first of all, we'll be seeing that how we can have this integrator with the help of capacitor. So here we have capacitor, here we have V, here we have I. So what is the voltage? If C is the capacitance and I is the amount of current through the capacitor, then what we can say about the voltage, V equal to 1 by C integration of I dt. V equal to 1 by C integration of I dt, and here we can write I equal to C dV by dt. So from these both expression, it is clear that if we want to make a integrator with the help of capacitor, then how can we achieve that, and also how can we achieve a differentiator with the help of capacitor, that is also clear. So first of all, in integrator, we are putting this capacitor at the feedback location. So at this feedback location, we have the capacitor and we have the resistance over here. So how can we find, first of all, what is the amount of current I input? The value of I input will be V input divided by R. Now we are aware that no current is entered into the OPAMP and all the current get bypassed through the feedback resistance. So what if I is the amount of current through the capacitor, then VC, the voltage across the capacitor, will be 1 by C integration of IF dt. Now IF is equal to I in, we have already calculated IF equals to I in, which is V input divided by R. So we just put this equation number 2, the value of current I in or IF in expression number 1. So we have Vc equal to 1 by RC integration of V in dt. So this is Vc. Now we need to calculate the output voltage. So I am applying KVL from this particular end to this particular end. So here we can see that V naught or V output is equal to minus of Vc. So V output equals to minus of Vc. We'll be putting the value of Vc in this expression and we are getting a result which is V naught equals to, or V out equals to minus 1 by RC integration of V in dt. So let's say if we are providing a square pulse at the input terminal of this particular op-amp, so the output expression or the output voltage will be something integrated form. So if we have a square signal, then the integration of this square is nothing but a ramp signal. Also, this negative sign shows that when a signal is going in upward direction, the output is going in the downward direction. Further, when it is in downward direction, then signal is going in upward direction because there is a phase shift between input and output. So this is the final expression for the integrator. Also we can write down some key points regarding this integrator, that output V naught equals to minus 1 by tau integration of V in dt, where tau is the time constant for a RC circuit. Now the time constant for LR circuit is tau equals to L by R. So we can have V naught equals to minus of R by L V in dt. So this expression we can achieve with the help of inductor. But the only thing is, while we are making an integrator with the help of inductor, then we need to place an inductor at this particular position and resistor at this particular location. Now the next circuit is differentiator. Or let me finish, let me give some further application of integrator is the low pass filter. Means we are having some cutoff frequency and less than this cutoff frequency will be passed by these type of circuits. So those circuits are known as low pass filters. Now we want to make this differentiator. So how can we make this differentiator? We just need to swap the location of capacitor and the resistor. So we can see here, and we'll be utilizing this particular part, means the current through the capacitor. So that is I equal to C dV by dt, means if the voltage across the capacitor is known, the current can also be calculated. Now we can see that this voltage is V in, and here the voltage is, let's say, due to virtual ground, this voltage is 0. So the Vc, the voltage across the capacitor Vc equals to V in minus 0, or what we can say, I input, which is the current through the capacitor, is C d Vc by dt. Also Vc is equal to V input. Now further, no current is entered into the op-amp. That means all the current get bypassed to the feedback resistance, and let's say VR is the voltage across the resistor. So VR equals to R multiplied by IF, and IF is equals to I input, which is C dV by dt. So this is equation number 1, this is equation number 2. We'll be utilizing this equation number 2 in equation number 1, and we are able to achieve VR equals to RC dV in by dt. Now RC is the time constant. Also, what is the relationship between output and VR is V naught equals to minus of VR. So the final expression is minus of RC dV in by dt. So again, if we are providing a triangular pulse, something like this, so we are getting a signal which is a square pulse or a rectangular kind of a signal. So the comparators is an electronic decision making circuit that make use of an operational amplifier. So these comparators are employed with a very high gain. High gain means, if we want to achieve a high gain, that means we need to have this open loop state. Open loop state means we don't need to place any feedback. So here we can clearly see that now the OPAMP is in open loop configuration with R reference, V reference. V reference means a voltage which is fixed at the inverting terminal, and also we have V input which is connected at positive, which is at non-inverting input. Now the condition is that whenever the input voltage is greater than the reference voltage, so the output will be very high and the output will be positive. So the OPAMP gets saturated and we are able to achieve plus VCC. Similarly, when input is less than V reference, so the output will be negative and huge negative output will be there, but the OPAMP will get saturated and the value will be minus of VCC. So we can say that this is a characteristics also, that whenever this region is known as normal linear region, whereas these two regions are known as the saturation region, because the OPAMP gets saturated. It will not increase the voltage, or the output voltage will not get increased beyond VCC and minus VCC. So these are the various applications of OPAMP. So we have seen that summing amplifiers are used in the audio mixers. Also they are used in the digital to analog converter. Voltage followers are generally used to isolate stages from each other, or also we have seen that voltage follower circuits or like unity gain amplifiers are employed in the impedance matching circuits. Again, this integrator and differentiator are having so many applications like low pass filter, high pass filters, and comparators can be used as the zero crossing detectors. So these are the various applications. After that, based on the applications of OPAMP, we have some examples. How can we calculate the range of the voltage gain? So again, the range of this voltage gain means it is a, first of all, it is a inverting amplifier, and the gain of the OPAMP is AV equals to minus of RF by R1. Previously we have only one resistance, but now we have R1 and R2. So we can write down this is RF divided by R1 plus R2. So the rheostat will work as, it will provide 0 ohm and 10 ohm. So it will give from 0 to 10 ohm. So accordingly we have two values of voltage gain, one with R2 equal to 0, one with R2 equals to 10 kilo ohm. We can easily calculate. Similarly, we need to sketch the waveform. So as it is clear that it is a integrator circuit and the output expression for the integrator is minus 1 by RC integration of V in dt. So if the signal is applied here, which is of a step signal of 1.5 volt, this is input signal. So accordingly we can plot the output signal also. So if the input is positive, so definitely the output will be negative. And we have seen that since it is a square, it's a constant value, so the output will be a ramp type of signal which is going in the downward direction. So we just need to put the values of C and R. Next example, it's a summing amplifier, and the output expression for the summer is minus of RF. RF is given, which is 330. V1 0.2 divided by 33 plus 0.5 with negative sign divided by 22 plus 0.8 divided by 12. We can easily solve this. This is the output of the summing amplifier. And finally we have the last circuit. For this particular huge circuit, how we can calculate? The question is quite easy. It's a OPAMP number 1, OPAMP number 2 and OPAMP number 3. OPAMP number 1 is a non-inverting amplifier and the gain of this non-inverting amplifier is 1 plus RF by R1, or the output is 1 plus RF by R1 multiplied by Vin. Here the output is same as Vin V1, which because it's a unity gain amplifier. And finally this third OPAMP is a summing amplifier. So in this way we can achieve the output of this particular circuit. So these are the references. Thank you.